Usually when we write functions, y equals f of x, we only have two variables, x and y, x being the independent variable, y being the dependent variable. But if our function is a composition, say g of h of x, we could think of the output of h, the inner function, as being another variable. What should I call the other variable? It's traditional to use the letter u. Let u equal h of x. U is going to represent the inside function. If I do that, if I define a new variable effectively to represent the output of the inside function, I also could think of f of x as being g of u if I liked, where u and x are related by h. It's a little weird, but you will see this kind of thing done in science classes to introduce a new variable like this. When you write the chain rule using this new variable u, and if you do it in Leibniz notation, something kind of interesting and convenient happens. We're after dy dx, the derivative of y with respect to x. By the chain rule, okay, well, that's f prime of x. By the chain rule, that's g prime of h of x times h prime of x. That's what we already know by the chain rule. Could I write these with Leibniz notation for the derivative? Yep. H prime of x, if u is h of x, that's the same as du dx. Right? If I've defined this new variable u to equal the output of h, to equal h of x, h prime of x would be the same as du dx. It's as if you don't have any y's anywhere in the problem. What about this thing? G prime of h of x. Wait a minute, h of x is u, that's the same as u. This is the same as g prime of u. Go back up here and just think about the fact that y also equals g of u. This could be represented as dy du. So with Leibniz notation, the chain rule becomes dy du times du dx. And that's convenient, you might say, because even though I've told you before these things are not fractions, I've also said it often doesn't hurt to pretend they're fractions. And if you pretend these things are fractions, it's like you can go from here to here by canceling the du's. Is that a rigorous proof? No. But it's nice. It's a convenient fiction. Remember I said calculus is full of convenient fictions? This is one of them. To pretend you can go from here to here by canceling the du's. You're not really canceling them because these are not really fractions, but it doesn't hurt to pretend. That does hint at a slightly more rigorous argument that is given in the book, involving, instead of dy, dx, and du, delta y, delta x, and delta u, which are not infinitesimal quantities like these things are sometimes imagined to be. Even the book's argument is not completely rigorous, though, because it kind of skirts issues of like, what if you ended up dividing by 0 sometimes? It's just a heuristic argument. I don't have time for it. To end class in 1 minute, I just want to apply this form of the chain rule to one example. Let's go back to actually, I won't do the sign of it, but I'll do e to the x cubed. If you think of x cubed as being equal to a new variable, u, then really these equations imply y equals e to the u as well, which equals e to the x cubed. And if we're after dy dx, and we're thinking of it in terms of what do you see up here as dy du times du dx, I can do those derivatives individually. dy du is the derivative of this one. That's e to the u. And du dx is the derivative of this one. That's 3x cubed, or 3x squared. But wait a minute, that can't possibly be the final answer, because I don't really want any u's in the final answer. Well, that's okay. Use this equation again right there. Replace u with x cubed. And there you have the final answer, which would be the same thing you would get if you did it the other way. I know that went by kind of fast. Maybe you were zoning out. I've been there. I've been in your shoes. I've been there sitting in math classes zoning out before. I hope you at least wrote it down and take the time to think about it after class and do the reading and think about it. Lots of examples in the homework.